Hi, this is our project for ABE 423. I'm Alexandra. I'm working with Andrew, Bryce, and Michaela. We're modeling a bioreactor for the production of monoclonal antibodies. Monoclonal antibodies are increasingly used for therapeutic treatment and diagnostic technologies with applications in cancer and autoimmune diseases. This project is going to focus on the production of these monoclonal antibodies by modeling a bioreactor system for the mammalian cell culture. Differences in accumulation are determined due to changes in bioreactor type, as well as the quality or productivity of the bioreactor. The assumed bioreactor consists of a cylindrical mixing chamber where the cells are cultured, an input for fresh media, and output line for waste removal. The mammalian cell lines typically associated with monoclonal antibodies are anchorage dependent and therefore sensitive to shear forces. For this reason, the program initially focuses on the fluid dynamics within the bioreactor. The model calculates the power number and the mixing time for the reactor, and from there develops a cost to power the reactor. The next phase of the model examines the factors affecting the growth of the cells in the bioreactor to determine the specific growth rate and the final number of viable cells. The glycolysis phase of the cellular metabolism in culture is also modeled. From there, the antibody production of the bioreactor was modeled, and the theoretical product yield is calculated. Finally, we're going to model output, a rough approximation of the profit that can be expected from this bioreactor. Throughout the program, the user has input control over variables such as media type, cell line, the initial number of cells and metabolites, bioreactor dimensions, time spent in cell culture, and more. Next, we're going to just give you a brief overview of our agenda. We're going to start off with looking at our accumulation, move on to productivity, Reynolds number versus power number relationship, cell growth modeling, glycolysis modeling, antibody production, and finally the profit of our bioreactor.
All right, Michaela here. So there are many different types of bioreactor designs. Here are just 3 out of many. This first one right here is a batch reactor. The second one is a fed batch reactor, and then the last one is a flow reactor. So for a batch reactor, it is basically just when we have a impeller and they're just mixing up the solution, and then the fed batch reactor is when the impeller is stirring up the media, and there is media coming inside as well. So that's why it's fed batch. And then we've got the flow batch reactor, which is when we have the media being stirred, media entering, and media exiting. In our project, we focused on the flow batch reactor because it was in steady state, so volume didn't change, and we were able to, the numbers were just a lot nicer to work with. And so here I'm looking at the accumulation, and accumulation is just roughly defined as the inlet minus the outlet plus the production inside the bioreactor. So this is just a formula describing all that. So you've got the flow, the concentration of the media entering, the flow out, the concentration exiting, and then just the rate times the volume. And so here's the pictorial version, again, inlet, the media inside, and outlet. And so the accumulation is different for each reactor. We've got the batch, and because there is no inlet or outlet, all we have is the production. So this is the full out version, but we are because there's nothing entering and nothing exiting, we're assuming that volume is constant. So if we simplify this, we get this equation right here. And then for the fed batch reactor, we've got something entering but nothing exiting. So from the general equation, we are able to disregard the outlet version, and we get this equation. So the inlet flow times the concentration inlet plus the production times volume. And then the continuous flow stirred tank, which is the one we're working with, because it is in steady state, the accumulation is 0. And so therefore, the outlet equals the inlet plus the production. And I have some code to represent this. Let me find it. It's up here. So here is the batch reactor, and here we have an input. Basically, we ask you what kind of bioreactor you're using, but for us, we're just using the third one, which is the CSTR, the flow reactor, and so we just skip over these two blocks of code because this first one is for the batch, and then the second is for the fed batch. And so for the third one, because it is steady state, the accumulation is 0, so we have an output saying that the system is in steady state. However, if we were doing the batch reactor, some equations, some variables that we need to put in are the temperature, because temperature does affect the accumulation, and then the initial rate, the gas constant, the time, the optimal lifetime, which is how long it takes for the reactor to produce a good amount of product. And then this K constant, which was defined in our text as this equation. And so with all this information, you find that your accumulation is the same as your production rate. And then for if it was a fed batch, again, you have all the same variables from before, but we have two new variables that are going to affect the accumulation: the inlet flow and the concentration of the media coming in. And again, here is the output. And so the quality of the bioreactor is viewed in two ways. The first way is the cost of it. So if it's cost efficient, or if it doesn't cost too much to make so much, then that is a good bioreactor. Another way we can measure the quality of a bioreactor is by its productivity, which is defined as the total moles of product produced by 1 mole of catalyst. A catalyst can be like an enzyme or a whole cell, and it can be many different things. So the first type of productivity we can look at is the productivity of the biocatalyst, and that is defined by this equation right here. We've got the yield of the product, the rate, and the concentration, and it is an integral, so you can integrate from 0 to t. And most of these values you can find from data collection, but R, the rate of productivity, is usually in an equation, so that is not as easy to find. The second one is through a volumetric productivity. That is in terms of mole or a mass per volume per second, and it is the average production capacity per unit volume. It is related to the productivity of biocatalysts. You can multiply the productivity of biocatalysts by the concentration and divide by time. That will get you your volumetric productivity. And the last form, and then we can also find the end concentration of the product after a certain time t. So yeah, you've got your yield, your rate, your volume, and your flow. So if we look at the code for productivity, we can see that we have some inputs in here. I've already put in some values in here just so that we can get through this quicker. I selected a temperature of 305, and because temperature does affect the productivity, and then we've got the concentration of the substrate, and then a volume of the bioreactor in meters cubed, the inlet flow, and the gas constant, yield, And we want a value of less than 1 for the yield because you can't have a yield of over 100%. And the yield is the total mass of product produced per total mass of substrate. And then we've got the constant. Most of these variables affect the constant, which affect the productivity. We can see that in the productivity equation right here, KD. And so this is what you get for the productivity with these values, and we're going to run through the code later and we'll see actual values for these. And then we can also calculate the optimal lifetime because that's dependent on the constant K. And then the constant K is in terms of seconds, and so we can convert this to days by dimensional analysis, and then we convert it to years, which we then use for the volumetric productivity because we want it in terms of years. And the volumetric productivity is just the productivity of the biocatalyst times the inlet concentration divided by the optimal time, a lifetime. And then we've got we can calculate the final concentration of the product, which in this example we were working with is fructose. So it's just the yield times the rate concentration times the volume divided by the flow. And then you just print out all of these. It tells you what the productivity is of the biocatalyst, the operational lifetime, and the volumetric productivity, as well as the end concentration. So that's it for my part of the code, and we'll move on to the next person.
Hi, this is Andrew Darkangelis. My part of this project was incorporating the fluid mechanics of the bioreactor and how that ultimately affected the power to run the bioreactor and the cost of it. So here you can see I have a few different types of impellers. These are standard ones. You have the anchor, propeller, 6-blade disc turbine, and so on. And so the propeller or marine impeller is the most common one, and it had the most data on it that could be found. So we chose to use the marine impeller in our bioreactor. So here you see a graph, and this is Reynolds number versus power number. The green line representing the transition from laminar flow to the transition flow, and then the red is the cutoff from transition flow to the turbulent flow region. So this is the relationship to find your power number based on what the desired Reynolds number is for the bioreactor. And the relationship in the laminar region has a negative linear slope in a log base 10 versus log base 10 graph. So that's another important thing to note about this figure if you look at the X and Y axes. And also the power number in the entire turbulent flow region is a constant value, so that's important. So anyway, the major challenge in finding this data was using point slope formula and linear approximations to come up with this graph in MATLAB from this graph found in peer-reviewed literature here on the left. So I'll talk about that in a little bit of how I did that and how I found for every Reynolds number the power number. So here's the basic setup for finding that relationship. Because it wasn't a linear relationship, it was a logarithmic relationship. So here's the basic formula. Log of y is equal to the slope times log of x plus the y-intercept. And here I've rewritten it to show in terms of power number and Reynolds number. And so now here's the expression for finding the slope of each individual line, which is just rise over run. So this was found by taking known points and finding the slope. So those known points, those were approximated graphically through this left-hand figure right here. And then those points were plugged in, the slope was found, and then from there, the y-intercept was found for that specific line. So as you can see here, there's a little break right here. So this represents a line. Then there's two different lines within the transition region, and then one horizontal line within the turbulent flow region. And so this graph just shows after the user inputs their Reynolds number, it outputs this graph that shows where their power number is. And this is just to, this is for the user's verification that what they're entering is indeed the correct power number. So here's some more important equations that I used, and these were all or the final power for the bioreactor was dependent on all of these equations. So I'll show you in a little while how these all fit into my code. So the volume of the tank needed to be known, and that depended on the tank diameter and its height. Then the rotation rate N, it was dependent on Reynolds number, viscosity of the media, the diameter of the impeller, and the density of the media. The circulation flow is the flow just off the blades of the impeller, and that was used to find the flow number. And really, this isn't entirely correct. This is a proportionality, and we had to assume the proportionality constant is 1 because we weren't able to carry any experiments out to actually find this proportionality constant. And then the mixing time is here at the bottom, which was dependent upon the volume of the tank, the flow number, rotation rate, and the diameter of the impeller. So now I'm going to step over to my code. So here's where my code starts. I just labeled so the user knows all of the different variables that they're working with. And so here's where I start to map out the graph. So here I guess I'll run this so we can have the graph come up. Okay, so here's the graph that we care about. So each of these values that I have written here, the known RE, known power number, those all correlate to a value that was plotted on this graph. And then these next lines were just used to draw these vertical green and red lines. Now here's my slopes of the various portions of power number versus Reynolds number. Here, I'll move this out of the way. And then here I just explain how I determined it. And then we have our input Reynolds number. And here's the bulk of the code. So it uses if, else if statements to determine the which line equation it's going to use to calculate the power number. So right here, if the Reynolds number is less than 100, then the MATLAB will use this equation for power number, and it will print that. And then if it's less than 1,000, it will use this formula and so on. And once it does that, it will print a star like you saw before on the graph. So I'll just show you this one more time. Oops, didn't pop up. So, and yeah, so then it will output this star right here to show the user where their power number is. So then moving on from that, here's the other different parameters the user will input: the tank diameter, the height, and then a statement that shows if the height is less than twice the diameter, it's not a legitimate, there aren't legitimate dimensions for a bioreactor. And then the other different inputs, and then mu is the dynamic viscosity of the growth media. At 37 Celsius, these were the found values from peer-reviewed literature. And we have 3 different inputs of common media with their different values. So what's important in my part was the mu value. And then with that information, it will pass it on to the last set of equations that I talked about in the PowerPoint. And then MATLAB will print the mixing time, as you can see here on the left-hand side. This was the time to mix uniformly. And then it will also print the power for the bioreactor. So for in this case, the bioreactor will require 400.85 kilowatt hours of power. And then at the very end, you can see on this line, it prints out the cost estimation based on Tucson Electric Power Company to run during the summer, because the summer's coming up. So the electric bill is going to be cheaper, and it will cost $47.10 per hour to run it during Tucson, or during the summer in Tucson. Okay, so that was my part of the bioreactor model. Thank you.
Alrighty guys, my name is Bryce and I did the cell growth modeling for this project. So to start off, I did the specific intrinsic growth rate. I found this equation here online on a article, and it models the specific growth rate for our cells. As you can see, it inputs the concentration of glucose, glutamine, asparagine, concentration of O2. It takes into account pH, our pH saturation coefficient, as well as our temperature and temperature saturation coefficients. UG is our sparging rate, and N is our speed of our impeller in our bioreactor. N max is the maximum that impeller can go. And then of course we have our inhibition constant for glucose, our concentration of glucose again, inhibition constant of glutamine, concentration of glutamine, inhibition constant of asparagine, again asparagine, and those repeated here. KD is actually the saturation coefficient for each one of these. Then we have K of O2, which is again the inhibition coefficient of O2 plus the concentration of O2. We incorporate this in the logistic growth model. You can imagine R right here as being the intrinsic growth rate. So we're able to model the growth rate of our cells using the intrinsic growth rate and then plug it into a Euler here. Okay, so this is the Eulers. I'm going to go back one sec though really quick. So I actually made 2 sets of code to model our cells. I did an ideal case where our flow bioreactor, the substrates didn't change. You know, supposedly in a flow bioreactor you're allowed to monitor the substrates throughout, and supposed to keep them relatively constant, but in reality this never actually happens. So I actually modeled our change in concentration here relative to glucose, asparagine, and glutamine, and our lactate and ammonia increasing as the number of cells go up. But I'll show that again later on in the code. Also in the realistic model, I took into account the shear stress relationship. Now it's important to note that in this, in our case, we're not considering detachment of our cells, so we're saying all of our cells are going to stay on. And of course, this isn't completely realistic, but if you seed your cells correctly and in a dense manner, you should be able to get them to stick pretty well. So what I've done here is I've taken the slope of these relative LDH activity. That's actually an enzyme in our cells. I've taken the slope of this over time, and I've actually scaled our population rate based on these values. But again, I'll show that a little later on. Here's a shear stress here, and this is the velocity that we eventually have to plug into shear stress to get the volumetric flow rate Q. Again, here's Euler's, which I'll go back to into our code once we get to the PowerPoint. And here's our growth curve. So we have a realistic model here. We have time and hours on the bottom. Now it's important to note that we have a relatively large bioreactor, so we're reaching confluency. That's the most dense your cells can get, around 550 hours in the realistic model. Whereas in the ideal model, we're reaching it, just under 20 days, 17 days or so, which is realistic compared to this model over here with our CHO growth. If you can see the square dots here, actually the CHO growth, and they're growing exponentially here. They haven't quite tapered off, and they've been growing almost 18 days. And again, I just threw this S curve in here just to show or exemplify our growth curve that we are modeling. All right, so I'm going to go ahead and show you the code next. All right, so I'm in my ideal model right now. What we've done is inputted 3 common types of media and their substrate values for each, so that the user doesn't have to input everything. But ideally, if you don't actually have the same media that you're using that we have listed here, you can input it down on the bottom. It'll say this isn't a program media, and you can program what you want into it. And that even feeds on down here. We have all of our constraints for the reactor. We went ahead and put in sample values for each one of these, but ideally the user would input their own values. And then we go ahead and get into our Euler's. So I have a time step of 2.5 hours right now, and that's running 2.5 times 240 time steps, so we're getting around 25 days. So here we have our concentration of cell matrix. We have our initial value of seeded cells. I went and put 100,000. That's a pretty common value. We have our maximum number of cells. This is the max cell density times the volume, and I've scaled it there. And then we have our O2 concentration. This is the sparging rate, UG, times the amount of time it's going to be in the bioreactor. So as you can see here, I have that really complicated equation for intrinsic specific growth rate going all the way to the back there. And that gets plugged into our DC dt, which we run our Euler's through. So we multiply it by our time step here. This is a logistic growth model, so we have amount of our population here times our specific growth rate times 1 minus our population divided by the maximum amount of cells we can have. So this is what actually limits our population here in this section. And then, of course, we're running the Euler's, so that adds the next step on. And then we plot our model, and it should look something like this. Oops, I'm plotting Alex's as well already. So there we have the ideal model. And then if we go to the realistic, we can plot, and we get something, or we don't, like this. There we go. So I don't know if you saw the first one. The first one reached confluency about 500 hours. This one's going to reach confluency around 800 hours. And again, that seems quite a long time for cell growth, but since we do have quite a large bioreactor, if I go back up, we can see that we have a 2 meter high by 0.75 meter wide bioreactor. So you can imagine a 6 foot tall bioreactor that's almost 3 feet wide. It's going to take a little while to reach confluency. Alrighty, I think that's going to conclude my section.
I'm Alexandra, and I'm going to begin by discussing the glycolysis model. Glycolysis is the metabolic pathway that converts glucose into pyruvate. As you can see, there are several steps in this process, several of which are enzymatic, so they require ATP and convert it to ADP. The arrows here represent the flux from the substrate to the products, and in some cases, these reactions are in equilibrium with a flux going back and forth. So we're going to take a more in-depth look at the equations that govern these fluxes. So the first flux equation for V1, which as we saw was using ATP to convert glucose into glucose 6-phosphate and ADP. The first constant is the maximum velocity of that reaction in the forward direction. Then we're looking at the change of ATP concentration over time multiplied by the initial amount of glucose. These constants down here are the Michaelis constants. They represent the relationship between rate of reaction and concentration of a substrate depending on the affinity of the enzyme for its substrate, and it's an inverse measure of affinity. So this is the affinity constant for ATP, glucose, and so on and so on. I have exemplified here a couple of those flux equations. So following from start to beginning, we're going to be looking at the change in concentration of those byproducts. So first, we're looking at glucose 6-phosphate, and then the change in concentration of fructose 6-phosphate, the change in concentration of ATP. So the way that we're setting up these differential equations is basically with mass balance equations. We're going to be following ATP or whichever said compound throughout the pathway. So from ATP, we see that we have the flux to ADP. So in our ATP reaction, as the reaction goes forward, we're going from ATP to ADP, meaning we're losing ATP. And so the flux for that equation is going to be negative as we're losing ATP mass. And we're going to follow that throughout the entire kinetic pathway for each of the changing metabolites. So it's basically how these differential equations are set up. In MATLAB, I solved them using the ODE 45. So I set up my flux equations. You can see them all here. Those are just the equations that we established using those affinity constants, maximal velocities, and initial conditions. So our output vector is going to be Y, which is the concentration for each of the metabolites that we're tracking. And then from these equations, we're going to put it into our ODE 45. So the user needs to input constants. We have here constants from academic sources, constants for the affinity and equilibrium constants, our time span and initial conditions, so the initial concentrations of each of these metabolites already present. Using the OD45, we're able to plot the change in concentration of each of these metabolites, which we have here. As you can see, obviously, glucose pretty much immediately shoots, glucose 6-phosphate, that is, immediately shoots up as we would expect. That's the fastest reaction, the one that's going to produce the most, because we do have that forward reaction and the equilibrium reaction, if you recall. And then as ATP down here is, you can just really see decreasing, our ADP is quickly increasing and then leveling out as it can, as it converts into AMP. So we have a comparison. We can see glucose rising immediately, and that decline in ATP. So next I'm going to talk about the antibody production in our bioreactor. From the growth model that Bryce made for us, we were able to find the amount of time that the cells are cultured, as well as the optimal cell density. We know this is the specific antibody productivity of whatever cell line is being used. That's the productivity specific to each cell line. So I used an example of a moderate specific antibody productivity in order to get the amount of the grams of antibody produced per liter over time in our bioreactor, using the by integrating this in MATLAB, as I can show you. Here. We're then able to just plot that against time, so you can see how your production is going as your cells are growing. So from there, we're able to get to our get our product yield at the end of the cell culture time period, and the going rate for these types of antibodies is between $2,000 to at least $10,000 per gram. So we used a conservative $4,000 per gram. This is another user input, so specific to the price of their antibody per gram, and have a simple calculation for a very rough estimate of how much it costs to power the bioreactor, the media cost for maintaining the culture, as well as the cost for the initial flask of cells. So subtracting these costs, assuming that you already have the bioreactor built, so not taking into account costs for building the bioreactor, the model is able to produce your approximate profit for the bioreactor. So running it with the conditions that we specified, we should be making a profit of about $22 million per batch of these monoclonal antibodies. So that's it for our project. Thank you.